Cast is now starting. All attendees are in listen-only mode.
Hello again, everybody. Thank you for joining the webinar. I hope you are all doing well. Just in case you've lost track, it's Wednesday, April 22nd. My name is Lisa Travers, and I am the Director of Marketing for Alliance. I am pleased you could all join us today for the second webinar in our public safety series. A few housekeeping notes. If you missed the first session and would like a link to the recording, you can send me a note and I will get it to you. I still owe some people a PDF of the presentation from last week, and if you want this week's presentation, send me a note. We will rerun the webinar series starting May 20th, so if you missed the first session, you can always sign up for that. And I will send out the invite to that in early May, which is not that far away. Today, we will take questions throughout the webinar, but Dawn prefers to answer them at the end. So please submit them as you think of them via the GoToWebinar console, and we'll read them out at the end. If we can't get to them all, we will follow up with you after. And a final note, we are recording the webinar, and you will receive a link to that afterwards in a follow-up email. So now I would like to hand things over to Charlie to introduce our speaker.
Thank you, Lisa. Good afternoon, everybody. I'd like to welcome you to our second session in our series of 3 on public safety. This is Charlie Schulz. I'm responsible for the in-building and public safety program here at Alliance. Those of you who were with us last week, we dealt with a high-level introduction, going over some of the general requirements and code considerations and very high-level stuff. And as promised, this week and next week, we're going to be drilling down a little bit deeper. For session 2 today, we're going to feature Don Henry with Comba Telecom, talking about the RF system design considerations. We're going to get a little bit more technical, not too deep, but definitely a little bit more meaty than last week. And of course, next week, we're going to wrap things up with system testing and best practices with Dave Adams from PCTEL. That's going to be a key one you want to sit in on, because testing is probably one of the most important aspects of a whole ERRCS deployment. So with that, I mentioned Don Henry. He's the Vice President of Sales for Comba Telecom, a very knowledgeable individual in the field. He too has a public safety background and very knowledgeable in the subject matter. So with no further ado, Don Henry.
Thank you, Charlie. And thank you, everyone, for attending. We hope this is going to be a good and fruitful expenditure of an hour of your time. Even though we're all working at home, we know everyone's still very, very, very busy. So again, we appreciate you attending. So I'm going to cover some things today, some of which Charlie covered last week. As Charlie mentioned, going to dig a little bit deeper. Some of what I'll cover today is maybe a little bit repetitive, but we think it's things that justify being mentioned a second time. As Charlie mentioned, I am VP of Sales at Comba Telecom. I'm also Program Manager for Public Safety. And as you might recall, last week, Charlie mentioned that he's got some personal interest in this subject as well, because of many, many years as a volunteer fireman. I also have a personal interest in this topic, because when I left the IT industry, before I got into the DAS industry, I spent a few years as a police officer, and I experienced a bad situation where my radio didn't work, and it's not very pleasant. So besides being my business, I have a real passion for this as well. Last thing I want to state before we move on is I'm pretty experienced, pretty technical sales guy. I've been doing in-building systems, primarily public safety, for about 13 years, about 8 of those years as a system integrator. So I'm pretty experienced, but I'm not an engineer. So as Lisa mentioned, we're going to ask you to hold the questions till the end. And if there's any questions that I can't answer, one of my last slides has the email address for Comba's Director of Sales Engineering. And any questions that I can't answer, you can address to him via email. And yes, you will be getting a copy of today's presentation when we're done. So I want to start by talking just a little bit. And again, Charlie talked about some of these things. We're going to dive a little bit deeper. I'll make this quick. So what drives public safety and building need? It's typically ordinances. Ordinances are typically part of building code, either city or state. In most cases, they're the fire control section of the building code. They typically apply to new construction or major renovation of existing buildings. Some jurisdictions now are requiring all commercial buildings over a specified size, even if they're already existing and even if they're not going through major renovation. Ordinance apply to buildings of 3 or 4 above ground floors or more, and or any subterranean area with people. You read that to mean parking, underground office space, underground retail. Ordinances typically require in-building signal, receive signal strength of a minimum of negative 95 dBm or decibels per milliwatt. They generally want coverage over 95% of the area. And if they don't satisfy those requirements, they don't issue a certificate of occupancy and the building owner can't move in. And note that these areas typically include stairwells, mechanical rooms, elevators, places that typically on a cellular DAS no one cares about. But of course, think about the first thing the firemen say is don't use the elevator, go down the stairwells. Well, obviously, if the fire authorities are going to be assisting people to exit the building, they want the radios to work in the stairwells. Typically, ordinances do not state that all new or renovated buildings require a public safety DAS. Very important to understand that. They do state that the building must successfully pass two-way radio communications, and the way we build buildings today, they never do. So pretty much it does mean that most buildings will require an in-building system. Lastly, most ordinances are based on, or at least have heavy influence from NFPA, National Fire Protection Association, and or IFC, International Fire Code Council standards. Continuing on, the HJ could be the city or a county agency. They're typically part of the fire authority, although they can be part of other agencies. They typically define the specifications contained within the ordinance. But be aware, many times the HJ, they don't always know, or nor are they the correct source for technical information like channel information, how much power to be delivered to the tower, etc. So if you don't have that, you're going to have to dig. Typically, they are responsible for testing and sign-off for the public safety DAS. And again, Dave Adams from P2Tel will go into that in more detail on next week's installment. Typically, they are the gate for issuance by the city or the county of the certificate of occupancy. And important to note, the HJ may or may not be the licensee. The licensee is who owns the FCC-issued license for the network. And if the licensee, they are required to have express consent of the licensee to authorize putting that ERRCS system on the air. A little bit about NFPA and IFC. Again, NFPA and IFC, these groups provide standards and guidelines. They provide standards and guidelines on NEMA enclosure and UL requirements, standby power requirements. They provide standards and guidelines on installation and commissioning of the equipment. They provide standards and guidelines on what area of the building should be covered, what the signal strength should be. NFPA, IFC are not involved in frequency assignments or selections. Understand that NFPA and IFC code is not the ordinance, but their standards generally, as we mentioned, are the basis for virtually all ordinances that are in use today. I've got a couple of slides here. Just want to quickly run through some basic terminology and definitions because we'll be talking about these things as I go through my presentation. So IB Wave or RAN plan, these are software tools that are used for creating an RF design for the ERRCS or Emergency Responder Radio Communication System. BDA is an acronym for Bidirectional Amplifier. That's a device that's used to receive and deliver radio signals between the network tower and the building. Fiber DAS is like a BDA, except it's a more elaborate system, and it's used to distribute the signal throughout larger and or multiple building sites. UL is an acronym for uplink. Uplink is the signal going from the handheld radio or the ERRCS system to the network tower. DL, an acronym for downlink, is the signal going from the network tower to the handheld radio or ERRCS system. Class A device is a BDA or a fiber DAS that provides individual filtering for individual channels. Those filters have to be 75 kilohertz or less in bandwidth. A Class B device is a BDA or a fiber DAS that provides wideband filtering across a number of channels. And I've got some slides later that go into a little more detail on this. And then last point on this slide, downlink and uplink gain. That's the ability of the BDA or the fiber DAS to provide a boost to the signal strength of either the downlink or the uplink signal. Continuing on with some basic terminology and definitions, link budgeting. That's the process of calculating signal loss or gain through the uplink and the downlink signal path, taking the attributes of each component of the ERRCS system into consideration. And again, I've got some slides that will graphically show this. Channelized uplink ALC, automatic level control. Automatic level control is the ability of the BDA or the fiber DAS to apply uplink gain. And in Class A case, it's ability to do that on an individual channel basis. And again, we'll go through that. Near-far problem. This is a problem you'll see addressed in more and more ordinances. This is a problem where if you have two radios in a building, one radio gets a signal out and the other one can't. And again, I've got a slide that will go through that. Isolation, that's the amount of signal reduction between the donor antenna on the roof of the building where the ERRCS system is and the nearest service antenna inside that building. And oscillation, this is a byproduct of insufficient isolation, can cause some problems. And again, I've got a slide later that we'll go through this. Again, want to remind everyone that this PowerPoint will be available as soon as we're done with today's installment. So I thought it would be important maybe to just quickly go through some of the basic components of a DAS. We're going to start with what's called a passive DAS. And a passive DAS consists of a bidirectional amplifier, as you can see here. It's connected to the donor antenna, so it talks back and forth to the tower. And of course, with all systems, generally require battery backup. So here we're showing a battery backup unit supporting that BDA. And then the BDA is to a passive network of service antennas, what we call the antennas inside the building. And this is a very simple diagram. The blue lines representing coax cable. There's many, many components that are involved in this. And again, I've got a slide later that shows that. Typically, a passive DAS is good for single buildings that are typically under 600,000 square feet. They're good for buildings that have conventional interior design, meaning a typical, 8 or 10-story building, vertical structure, straight hallways, sheetrock walls, buildings that are designed for office, residential use, etc. And they usually work very well in buildings that have very straightforward and easy to deploy pathways for coax and fiber. So again, a passive DAS is a BDA feeding service antennas. This next slide shows a fiber DAS. Again, very similar in ultimate function. You've got a fiber DAS head end connected to door antenna that sends signal back and forth to the network tower. Of course, the head end also has to be battery backed up. But now, instead of this device connecting directly to the service antennas, the device is connected over fiber, as depicted in the red line, to fiber remote units. These fiber remote units have amplification in them, and they in turn are connected to the infrastructure with the passive service antennas. And again, the fiber DAS remotes have to be battery backed up per ordinance. So again, we're showing the BVUs here. Fiber DAS, again, generally good for single buildings that are typically larger than 450,000 square feet. They're good for single buildings that have what I'm calling a non-conventional interior design. Conventional shaped buildings, many floors, difficult coax pathways, etc., meaning it might be easier in these buildings to locate fiber DAS remotes at various locations and run the coax from there, because you've got a very easy way to get fiber up to there where you might have a lot of difficulty getting infrastructure all the way out to these antennas. And of course, fiber DAS is really the only good solution for multi-building campuses or projects. Again, continuing on with some technology and terminology, I promised some slides that would explain this. So here's kind of what a Class B amplifier, this could be a BDA or fiber DAS, looks like. So what we've got here is we've got a number of 800 meg public safety uplink signals. The signals are depicted by those little red spikes. And we've got a number of public safety 800 megahertz downlink signals, again depicted by the red spikes. And in between them, we have uplink for 850 meg cellular. We obviously want to filter this out. So a Class B device allows some wideband filters depicted here by the green lines. So we've got a filter that encompasses all of the uplink channels, and we have a filter that encompasses all of the downlink signals. That's great. So what that means is we're going to keep this stuff out, but what's not so good is this filter, as you can see, will not only allow these signals to pass, but it will allow anything else within here to pass, and some of that you may not want. So Class B, the attributes of it is it's easier to set up in the software, and it's easier for future maintenance. What I mean by that is if a jurisdiction adds more channels, you know, as long as the original filter was wide enough to encompass those additional channels, nothing needs to be done. However, one of the bad things is both on the uplink and downlink side, in addition to the frequency through, unused frequencies can also be amplified. This can create additional noise, create additional RF traffic we don't want. And because these are wideband filters, you're not able to achieve some channel-based filters such as channelized AGC, automatic gain control or level control, and channelized squelch. The other thing to note about a Class B device is it must be registered with the FCC. And I know Charlie talked about that last week in his presentation, so I won't say any more about that. This next slide now shows a Class A amplifier. So note the similarities. We've got the same bunch of uplink channels for public safety, the same bunch of downlink. We have the same 850 meg cellular uplink in between. But now, instead of putting in a filter that covers all of these, note, again, the red spike indicates the desired channels. The green around those indicates the individual filters that we've put around each of the specific channels. So let me jump back. Again, with Class B, we had one big filter that covers all of them. With Class A, each desired channel has its own individual filter. So what are the attributes of that? Minimum noise will be created. You won't be passing any stray RF that you don't want because these filters will keep everything except the desired channels that you want from passing through to the network. And again, because of channelized features, channelized Class A, we can have channelized automatic gain control or automatic level control, and we can have channelized squelch. Squelch, by the way, is a feature built into both Class A and Class B devices that allows you to minimize the noise that's being put on the network. And one of the things we always want to do in a good DAS design is keep the DAS from putting additional noise on the public safety network. The next thing I want to talk about is the near far effect, and I mentioned that when I was first starting. So what is the near far effect? So here's a typical Class B BDA kind of a situation. You got a BDA, it's talking to the donor tower. You've got some number of service antennas in the building. I've kept it to one for sake of explanation. Here's the problem. You've got first responders in the building. They each have their 2-watt handheld radio. One first responder is right under the DAS antenna. The other first responder is a long way away. So this guy's going to key up. His signal is going to go to the DAS antenna. It's going to go to the BDA. The BDA is going to say, holy moly, that's a really, really, really strong channel. We can't put that much strength out onto the network. So let's deploy automatic level control and let's reduce the signal. Well, okay, now what happens is this guy's signal gets reduced. It gets normalized, if you will. Now we've got a normal strength signal going out to the network. But the guy who is far away, by the time his signal gets to the antenna, it's already been greatly reduced. It gets passed to the BDA because the BDA put the ALC control over all the channels. Now this guy's signal is so reduced that he either can't get a call out at all, or the quality is so bad that no one can understand him. Now you have a problem. So that's very simply described, but that's what the near far problem is. How do you solve that? you can solve it a couple of ways. The best way to solve it is put in enough service antennas. We've seen situations where, again, we understand everyone's trying to keep the costs down. We've seen situations where systems are designed with a horribly insufficient number of service antennas. Good design practice says you should have a service antenna about every 50 to 60 feet, and that's based on a calculation of how many square feet of coverage a given antenna can provide to allow for the radio, no matter where they are, to be close enough to an antenna that their signal doesn't get diminished. So in this case, what we see is the 2-watt radio signal from the close guy and the 2-watt radio signal from the far away guy, they both get through at equal signal strength. And even if ALC is deployed, it's deploying it evenly across all of them, so all radios get a good signal on. So that's one way to solve the near-far effect. The other way you can solve it, and you do both, put in enough antennas, but in addition, if you have a Class A BDA, here's what can happen. Again, you got a guy right underneath the antenna, and you got a guy far away from the antenna. This guy keys up, signal goes in, comes over, the BDA says, oh my gosh, that signal's really, really, really strong. We need to reduce the strength of that signal. Because it's based on a channelized basis, it will reduce the signal on this guy, but it doesn't touch the signal for this guy. So therefore, again, both signals go out at a proper. So again, a Class A device can do a lot to help with the near-far problem. Again, we highly recommend do both. Put in enough antennas and put in a Class A device because that will help with this problem. Another thing I want to talk about is, and it's one of the slides that I did earlier mentioned this, isolation and oscillation. So isolation is the signal strength distance, if you will, between the donor antenna and the closest service antenna inside the building. Generally, this is going to be an antenna that's located on the topmost floor. Not always, but generally that's the case. And good design practice says you always want to have at least 20 dB of signal separation between the donor antenna and the service antenna. If you do, you generally have no problems. If you don't, here's what can happen. So first responders in the building, he keys up, uplink signal goes to service antenna, from the service antenna to the BDA, from the BDA out to the donor antenna, from the donor antenna out to the tower. So far, so good. However, even though Yagi antennas for donor antennas are directional, they still do leak a little signal off to the side. So if there's enough signal leaking off, that signal leaking off will get picked up by the service antenna, sent back to the BDA, and sent back out in conjunction with the original signal. This happens in microseconds of time. Now what you have is you have a signal that's a composite of the original signal plus the leaked signal going to the tower. It's too strong. And guess what? Now it leaks again from the donor antenna down to the service antenna, out to BDA. Now a combined signal goes out that's stronger yet. This keeps going on and on. This signal keeps increasing. And what can happen is can drive the amplifier and the BDA into what's called clipping, which makes the audio quality horrible. And if this signal gets too strong and has too much noise, it will actually do what's called desensitizing the radio that's at the tower and can actually take it down. Now nobody who's trying to talk to that tower can get through. And as you can imagine, the HJs don't like that at all. So very important when you're doing a design to plan for enough isolation, because if you do that, then you won't have problems with oscillation. So what do you need to know to start a system design? You need to know the local ordinance requirements. You need to know the frequencies of the bands to be covered. And in some ordinances, remember I mentioned earlier, they don't always know the exact channels and things. I've seen ordinances that say the system must support the local sheriff department. Well, okay, that's good to know, but what does that mean from a technical perspective? It means you need to find out what channels and what bands the sheriff's department runs on, you know. And so that should be in the local requirements. We're seeing the ordinances get better and better at this. but sometimes they're not, and you have to do the investigation, make the calls, and find out. Local ordinance should define what's the minimum downlink received signal strength indication. Remember earlier we talked about minimum of neg 95 dBm across 95% of the coverage area. That's what that refers to. What areas of the building need to be covered? What's the total coverage area of the building? What is the desired or required uplink signal that the ERRCS system will deliver to the tower? Is battery backup required? And if so, for what duration? We've seen ordinances say we want the thing to run for 2 hours if the AC goes out. We've seen other ordinances say we want it to be 24 hours. So again, these are all the things you need to know from a local ordinance perspective. And then also the construction requirements. Is conduit required? Is it required for the riser run coax only? Is it required also for the horizontal coax runs? You need to know that. Is 2-hour fire rating required? Sometimes they say we want the head end equipment, meaning the BDA or the fiberDAS head, to be in a 2-hour fire rated room. That's all they ask for. Other times they'll say, no, we want the horizontal coax to be 2-hour fire rated. So again, you need to know that because all these things will play into the design that you're going to do. Is plenum coax cable required? Some jurisdictions require it, some don't. Some require it only for the horizontal runs, some require it for the vertical runs as well. Is UL rating required? And if yes, just what we call regular UL, or do they require UL 2524, which is a new UL standard that emerged about a year ago? Is the network trunked or is it a conventional network? What is the measured downlink RSSI at the site? Have you been able to go to the site once you know what the frequencies of bands are? Have you been able to go to the site with some test equipment and actually measure it? Because the designer needs to know that, because he needs to know how much signal he's going to get at the building to plot his downlink side of things. What else do you need to know? The type and the density of the exterior walls. The type and the density of the interior walls. You know, are there, if it's a hospital, are there lead-lined rooms? You need to know that because nothing goes through lead. You know, are the walls sheetrock construction? Are they metal studs? Are they wooden studs? You need to find these things out. Is the exterior of the building done with low E glass? Most are. And for interesting anecdotal point here, low E glass has the same RF blockage characteristics as an 18-inch cinder block wall. So think of that. An RF signal is going to get blocked going through 18 inches of cinder block. It's going to get blocked just as much going through a window with low E glass. It's nice if possible to have architectural floor plans. The more detailed and better the floor plans are, the more the RF designer doing the system is going to love you. What's the square footage of the buildings you're going to be covering? How many floors require coverage? What is the type and amount of interior clutter? What interior clutter is everything inside the building. People, office furniture, filing cabinets. In the case of a hospital, you've got a lot of medical equipment that can be a real clutter provider, and hospitals, medical equipment also generate a lot of spurious RF. So again, the DAS designer wants to know all these things. What's the distance from the network tower to the project site? Sometimes the building is, you know, a half a mile from the tower. Sometimes the building is 15 miles from the tower. You need to know that. Find out if you can, are there any future plans for other tall buildings that are going to be built, you know, maybe a year from now that would end up being in this pathway from your donor antenna on the roof to the tower. And then other thing you want to know, specific requests or requirements of the building owner. They generally won't have any requests in terms of the technical side, but they may have some cosmetic and aesthetics concerns. Well, we don't want the antennas in this part of the building visible, which means you might have to build, you know, some kind of a structure to cover those antennas that won't affect the signal, but will hide them from plain sight. The other thing to know is you will very likely need to do an initial design. Then you'll need to modify that design and make adjustments after the pre-construction site walk. And one of the other slides I have here in a little bit will describe what I mean. What RF criterion should the design address? Obviously, compliance with everything that's required in the local ordinance. The design should ensure that the uplink signal strength and noise maximums match what the licensee is requiring. It should ensure that you're attaining the minimum required DAQ. DAQ is delivered audio quality. Charlie talked about that in his presentation last week. Typically, ordinances want a DAQ of 3 or better. The design should ensure that the downlink coverage requirements are met. Minimum downlink signal strength, coverage area that's required, specific areas that are required, et cetera, et cetera. The design should ensure that there's sufficient service antennas to provide strong enough uplink signal to the input of the BDA. And again, this also helps solve the near-far problem. The design should ensure that you have the minimum uplink gain applied to the donor antenna to help keep excessive noise off the network. The design should ensure that there's adequate DAS dominance to protect against TDI issues. Okay, what is DAS dominance? DAS dominance means that the signal from the DAS inside the building is going to be stronger than any signal that might be leaking through directly from the tower. That's what DAS dominance means. What is TDI? TDI is an acronym for time delay interference. And what TDI is when you have multiple signals, either to or from the ERRCS system, to or from the tower, arriving at the destination, but one is slightly delayed. The delayed signal can affect the original signal to the point where it's very garbles the communications. And if it's bad enough, it can actually totally cancel out the signal. So again, adequate DAS dominance, very, very important. And we learned this many, many, many years ago in cellular DAS designs, because the same thing applies to a cellular DAS design. The other thing that the RF design should address is to make sure there's proper uplink and downlink link budgeting. So now I've got some slides with less text and more pictures. So here's a schematic design example of a fairly simple and small BDA public safety system. So here's a BDA, here's the BDU. Here are the service antennas. In this case, happens to be low profile ones. Here are splitters and couplers. And I want to point you, and here's the donor antenna on the roof talking to the tower. So I want to point out a couple things here. If you look in this little chart, we see on this side of the line is power per channel in dBm, and on this side is composite power in dBm. I'm not going to make us go through this whole thing again. You can look at this PowerPoint later. But you'll see if you follow the signal path, each time it goes over some coax or goes through a splitter or coupler and ends up the antenna, you'll see that these numbers go down. Why? Because every foot of coax has some signal loss. Every passive device you go through has some signal loss. There are some passive devices that can actually increase signal, so those can be used in your design. And the antennas generally provide some level of gain. Again, gain means an increase in the signal. So now you see what I was talking about earlier when I said link budgeting. So when the designer is saying, okay, I know I've got this much signal coming in, I need to make sure that I have that minimum NIG 95 out to all these antennas. He has to design and plan for all this stuff, because everyone's going to add some loss, and this has to be calculated to make sure you get the signal at the antenna that you need. And on the uplink side, when that radio is talking to the service antenna, again, all these components are going to cause some loss, so that needs to be all calculated so that the designer knows he's going to get X amount of input to the BDA, and then that's going to turn into X amount of signal to the tower. And on the uplink side, the design even has to incorporate the signal loss from the donor antenna to the tower. That's called free air loss. So even though it's going through air, the signal loses something. So this has to be very precisely calculated to be able to deliver a signal through the tower that is going to make the call quality good, yet will not desensitize the macro, will not put too much noise on the network. This next slide is an example of a link budget table. So it's basically showing this information, but it's showing it in a table. And these kind of tables are exported once you've done the design in IBWave or RAN plan, then you can export the uplink budget table, and this is an example of what that looks like. So again, a lot of numbers, a very experienced, very senior RF engineer who I've learned a lot from over the years, is a good friend of mine. I can remember when I worked with him at a DAS integrator, and he'd have weekly meetings with the DAS engineers in a room with the door closed. I can always remember every meeting. At one point he would yell, "I keep telling you guys, it's all in the damn numbers." And that's exactly the truth. It's all in the numbers. It's all in the math. This next shot is this is an example of what a completed design looks like. So after the IBWave designer has put in all the parameters, he knows the downlink signal strength, he's calculated the uplink signal strength gain that he needs across system, etc. He's determined where the antenna locations have to be. He's laid in all the coax. You know, he's put in, you see these little things here, that's the splitters and couplers and all that passive kind of stuff. Remember I mentioned you'll probably need to update the design. Once he's done the design and then you do the site walk, you might find, for example, oh my gosh, we can't run the coax here like we thought. There is some kind of a wall here that prevents it. So that means this hunk of coax actually has to go here, down here, around here, and back. Again, remember that coax adds loss. So now the designer is going to have to do some recalculation and then end up modifying because of what you discovered on the pre-construction site walk. One of the things Charlie showed last week in his presentation, and in fact it was so great I just stole the picture from his presentation. This is an example of what will come out of the design package, and that's called, you know, propagation predictions, or commonly referred to as a heat map. So again, that's a different building obviously than the one I just showed. But here's the antennas, and as Charlie pointed out last week, the color indicates the strength of the signal. So any area place you've got red, you've got plenty of signal. Any place you've got green, you've got just about where it should be, even light purple, about where it should be. If anything showed on this map that was this color down here, you'd say there's a problem. We need to tweak the design because there's insufficient signal strength there. One thing I want to point out is that in IBWave or RAN plan, these heat map predictions, they show only the downlink. They do not show uplink. So just be aware that designs have to be done so that they don't only accommodate the uplink or the downlink requirements, but uplink as well. Okay, so what tools and talent are needed to create a design and to then test when and while the system is being installed? So for design creation, you need to have a package like IBWave or RAN plan. You need to have an RF experienced design engineer who understands RF, understands public safety networks, and can, you know, is certified to design an IBWave or RAN plan. And you need to have an RF experienced, ERRCS experienced, construction experienced project manager. Again, he should have a reasonable amount of RF experience so that when he's doing his site walk and he's communicating back with this guy, the two of them can speak the same language and he can relate back to the system designer what he's found so that they can work together and modify the plan to make sure it's going to be constructible and ultimately that it'll work right when it's done. From an equipment perspective, you're going to have a spectrum analyzer. You're going to have a signal generator. You're going to have some miscellaneous stuff, test antennas, jumper cables, adapters, attenuators, couplers. In other words, a toolkit that the technical people that are on site in the field can use. And you're going to have, for the test, you're going to have radios that are programmed to the specific test frequencies that the HJ will want you to use when you're doing your pre-test before the HJ comes in to do their final test or ATP acceptance testing plan so that they can then sign off in the building. So the last point on this slide is if all of this is a little overwhelming or something you're not either financially or infrastructurally prepared to do right now, but yet you do have opportunities because you've got relationships with electrical contractors or general contractors that you could grab a project like this and win it, consider partnering with an experienced ERRCS integrator who does know how to do all this stuff and does have all this equipment. Instead of you trying to get 100% and failing, find a qualified integrator and partner with him. You guys can do a whole bunch of systems and split the pie, as it will. So in summary, developing a proper ERRCS design that will result in a system that will be accepted is not difficult if you have the appropriate equipment, you have the appropriate experienced personnel, you've done the appropriate due diligence regarding ordinance and RF requirements. If you have opportunities but you currently lack the above, again, consider partnering up with an integrator or a design house who can do this design for you. If you do decide to choose a partner to partner up with, both Alliance and Comba, we know a lot of very competent, very qualified integrators will be very happy to help you find and select a good partner to work with. And again, doesn't mean you have to partner forever. While you're splitting some deals with some folks, you can learn. You can maybe get to the point where you can justify hiring the right people and getting your own equipment, and someday you'll be able to do your next project all by yourself. And this market is going to grow by leaps and bounds for the next several years. So, start out and do it right at first so you make sure you can be on a continual path for success. Lastly, if you need additional information on Comba's products, or you'd like a Comba sales rep to help you find a partner, again, in the PowerPoint will be the link to Comba's website, where you can, based on your state, figure out who your Comba sales rep and then reach out to them. Of course, as I mentioned, my title is VP of Sales, so I have to have one slide that talks about selling stuff. Otherwise, I'd get fired and Charlie would lose respect for me. So through our partnership with Alliance, we provide a complete line of equipment and materials needed for ERRCS solutions. We have BDAs, fiber DAS, Class A, Class B, varying power levels depending on how big the project is. We have solutions for both UHF and 700, 800 megahertz, and again, for venues from 50,000 to several million square feet. We have a complete line of passive components, splitters, couplers, combiners, tappers, all the things we talked about on the link budgeting slide. And we have a complete line of antennas, sort of the conventional cone antennas you've seen for many years, low profile antennas that cover multiple bands, etc. And we have donor antennas even for the rooftop. So about the only thing that Comba doesn't manufacture is the coax and the fiber and the connectors for those, but those are also obviously available through Alliance. So last slide. Thank you for attending the session today very much. We appreciate it. We're going to open up for questions. Again, as I said, I'm not an engineer, so if there are any questions that I can't answer in this presentation, is the email address for Matt Lunny. Matt is actually listening in on this call as an attendee, so he can tell me later how many things I said wrong. And he's our Director of Sales Engineering, so any questions that I can't answer, feel free to email those to Matt. And if you have any other general questions from the session that are maybe not super technical, questions about ordinance or what have you, that you think of afterwards, my email address is in here. Feel free to reach out to me as well. And then lastly, feel free to visit Comba's website at www.combausa.com. So thank you. I'm gonna stop talking now finally and turn it over to Lisa, because she probably has a whole bunch of questions that I can hopefully answer. So Lisa, back to you.
Thanks, Don. That was awesome. I do have a whole bunch of questions, so I'll start from the top. Oh, they're coming in quick. Is there a specific type of certification or licensing we need to look for from a designer?
Okay, that's a very, very, very good question. So first of all, let me talk just quickly. I'll answer that question and provide a little bit more. Right now is no certification that's really appropriate to integrators for the ERRCS business in general. There is a certification called GROL. That stands for General Radio Telephone Operators License. This is an FCC license that some jurisdictions want to see. It's really not directly related to ERRCS, as I mentioned, but it is give people a little bit of basic RF understanding. People can take the course online and then take a test, and if they pass, then they get a GRL. Many jurisdictions ask for that. Now, beyond that, for IB Wave or RAN plan, yes, I'm very familiar with IB Wave because every company I've worked with over the years has used IB Wave. Again, RAN plan is a very similar offering. I don't know a lot about that. Presume it's going to be the same. But with IB Wave, you take various levels of training from IB Wave, take a test, and then you get certified. So with IB Wave, for example, certification level 1, 2, and 3. 1 being the lowest level, 3 being the highest level, and 2 in the middle. Integrator says, okay, we're going to make the commitment to get an IB Wave license. Once you have that license, then you hire someone. Hopefully you'll hire someone who's already IB Wave certified at some level. Now they can take some additional training and get certified to a higher level. Or you hire someone who's got a very strong RF background. They've never done IB Wave, but they want to learn. Again, IB Wave can provide the training and the testing so that they can get genuine, legitimate certificates. And again, I presume RAN plan.
I don't know if everyone can hear Dawn, but if you can hear me, that's good, I guess. This happened to us last
Could no one,
Dawn,
Lisa, could you hear me?
Yeah, we couldn't hear you. We couldn't hear the end of that last question, but I can hear you now.
Okay.
Well,
again, whoever asked the question, if I was chopping up for some reason, again, feel free to just shoot me an email. And I'm leaving the screen up, by the way, so if those who say, I don't want to wait for the PowerPoint, you can write down our email addresses. So again, whoever asked that question, very good question. If you didn't hear the answer completely, shoot me an email, I'll answer it.
Okay, some people are telling me now they heard it all, so maybe it was just me. Yep, everyone said they heard everything you said. So I guess it was just me. The next question is related. Are there Comba products in RAN plan?
As far as I know, yeah. I don't know that they necessarily have the most update. So the files that we provide to IB Wave, for example, that has all our stuff in it are called VEX files, VEX, like Victor, Edward, X-ray. I don't know what they're called in RAN plan. I know that we communicate with them. So J.R. Wakabayashi, who is our marketing manager, who deals with both IB Wave and RAN plan, is on this call. So I'm going to presume that he can't answer the question, but he'll look into it and we'll get an answer back to you, Lisa, that you can then relay on.
Okay, that's awesome. Thanks. Oh, someone just responded and they said they are in RAN plan. They are called DDX files.
Perfect.
Okay. So next question, are there specific situations where using Class A versus Class B should be considered? Excellent question, I think.
Very excellent question, and it points out something I should have mentioned in my presentation. So, first of all, many jurisdictions mandate Class A. It's not an option. They say device must be, and I want to point out too, no jurisdiction will say use Comba or use one of our competitors. They don't do that, which is fine, but they sometimes will say Class A. If the ordinance doesn't specify, then it's up to the integrator to make a choice. And the choice is based on, okay, are there a lot of channels in use? Is this an area where there's a lot of heavy RF? Like, for example, downtown LA, you probably don't want to try and use a Class A device, a Class B device, because again, remember, Class B is going to let through not only the channels you want, but anything else RF that's within that range of that filter, it's going to push that through. So if the ordinance doesn't mandate Class A, then the decision is based on, a number of things. Are there a lot of channels that need to be relayed? Are there a lot of other RF things going on in the area that could be mixed in that we don't want? you know, in some situations, there's another thing called group delay. One of the disadvantages of Class A, because of the filtering mechanism, they tend to have group delay. Sometimes that can be a problem with the networks, so therefore you use a Class B. Again, I would say this: if an integrator is working a project and Class A is not mandated and they're having a difficult time figuring out which to use, again, feel free to reach out to any of the Comba sales directors, and they can engage Matt or one of Matt's people. We'd be glad to jump on a call and, you know, ask some questions and help the integrator figure out which is the right thing to use.
Okay, thanks. So the next question is, why does the roof antenna usually mount to a freestanding mount? That's from Scott.
Why does it usually mount to a freestanding mount? Okay, so let me answer that the way you said it was Scott?
Scott Wimmer, yeah.
Okay, hi Scott. I know you can't talk to me, but you can hopefully hear me. So I'll answer it the way I think you're asking. So generally, the way roof antennas are mounted, and it's funny because these systems can be fairly technically complex till you get on the roof and you see, here's the donor antenna. It's mounted on, you know, it's mounted on a 5 or 6 foot pole. That 5 or 6 foot pole is stuck in this big metal tripod, which kind of looks like a camera tripod, except it's metal, it's construction-y looking. Then that tripod is mounted to a wooden thing that looks like a pallet. It's called a skid. And then sitting on top of that skid are a bunch of cinder block bricks to keep it in place. And you go, oh, that sure isn't very fancy, but it works. Most cases, that's how a donor antenna is installed on the roof. And then, of course, the donor antenna has to be properly pointed to the tower. There are situations where the donor antenna, again, will be mounted on a 5 or 6 foot pole, but then that pole can be mounted to the side of a small building, like an equipment building that's sitting on top of the roof. We've seen it done where it's mounted to the side of a chimney. We've seen it done where the pole is actually mounted to a bracket that's mounted to the side of the building. It doesn't really matter. The key is you want to make sure that that is in a position where it's got a very clear, unobstructed line of sight to the tower. So Scott, if I didn't answer your question, again, shoot me an email, and in your email, include your phone number. I can even give you a call.
Thanks, Don. So the next question is public safety DAS only driven by BDAs, or can it be an RF source?
Okay, again, I'll answer that the best I can. The only way you could have an ERRCS system that would not have a BDA or a fiber DAS, in fact, no, let me step back. The only way you could have a system that didn't have a BDA would be if the jurisdiction put basically the same equipment that they have at the tower on site. In the cell world, those are typically referred to as BTS, base transceiver station or base station. So on really big important venues, like when they, after 9/11, when they rebuilt the World Trade Center thing, they put in the DAS, but they said, we're not going to have this fed off air. They actually, NYPD and New York Fire got together, and they actually put base station inside one of the buildings. That happens on occasion, but I would say probably 99% of the ERRCS systems across the country always have the BDA, which again talks to the donor antenna on the roof, which again talks to the tower. Now, you could have a base station on site as an RF source and have that feed a fiber DAS. So if it was a multi-building campus, they're not going to put a base station in each building. They could put a base station in one building and have that base station feed the fiber DAS instead of a BDA feeding the fiber DAS. But again, the amount of times that they put a base station on site is very few and far between. Part of the reason being that base station really is part of the network. And so that means the jurisdiction is going to have to be responsible for paying for that base station, installing that base station, managing that base station, maintaining that base station, and they generally are not equipped to do that. So again, 99% of the time, it's always going to be a BDA.
Don, I've had a couple of comments that I'll add. Somebody mentioned that it's called BTS Fed, and Matt from Comba commented, he said, typically only places he's seen them is extremely high profile venues for safety, such as the Pentagon, train tunnel systems, because the cost is way too high to have a dedicated BTS for public safety at different buildings. Thanks, Matt.
Yep. Yeah,
So,
thanks, Matt. And that supports what I said, because remember I said when they built the World Trade Center after 9/11, that's what they did. They put in a base station. So again, it does happen from time to time, but it's very, 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 very few and far between.
okay, so we still have a lot of questions. How do you determine which level on splitter to use? I think maybe he means which levels to use splitters. Not entirely sure. Maybe, Bill, if you can reword that and send it in again, maybe that would help us. The next question from Chuck is, what about the use of radiating cable?
Radiacs, or as it's commonly referred to, leaky coax. Leaky coax has its place. For example, let's say you're putting a DAS in and you've got to cover a tunnel, and it's a train tunnel, and there's not a lot of space between the train and the tunnel, and the tunnel is not a rectangular structure, it's a round structure. You say there's really no way to put in antennas, so then you'll use leaky coax. And what leaky coax is, well, let's step back. What regular coax is regular coax is designed to keep the RF signal trapped inside the coax, so it can't go anywhere until it gets to the antenna. Then the antenna is what radiates the signal. Leaky coax is designed to intentionally leak the signal, because instead of having the coax feed a signal to an antenna, you want that coax to sort of be the antenna. So leaky coax does exist. It does have its place. The problem with leaky coax is, remember, you also have that same potential for signal loss. Every foot of coax has some loss, as I mentioned. Same thing with leaky coax. So if you have a 400-foot length of leaky coax, the signal at the end of the coax that's connected to the BDA is going to be much stronger than the signal at the end of that 400 feet of coax. And because it's just a straight hunk of leaky coax, you can't do anything to compensate for that signal loss. So it works okay. There are applications for it, because again, if you can't put in antennas, you don't really have a choice. But the other thing to point out is, if you're using it in tunnels, this is interesting. I'll just share this. If the vehicles in that tunnel are electric vehicles, like maybe a transport train at an airport, no problem. But if the vehicles in that tunnel are petrochemical fuel, like cars in a tunnel or trains in a tunnel, leaky coax gets destroyed very, very quickly, because by nature of the fact that it's leaky, it's leaking RF out, but also things in the environment can leak in. So exhaust from petrochemically fueled vehicles will get inside and literally destroy that leaky coax within a matter of months. So again, it's okay in a tunnel if the vehicles are electric powered, not okay in a tunnel where the vehicles are, fuel powered vehicles. And again, it has its place, but you very rarely see leaky coax used unless you have no choice. Now, we've seen situations where an integrator says, well, I want to keep the cost down, so I'm going to use leaky coax. We recommend against it. They go ahead anyway. They put it in. The system fails because the signal quality is so sporadic and bad. So we don't recommend it again unless you have no choice.
Yeah, someone just asked, is leaky coax recommended for UHF applications?
Well, again, if you have no choice, if you can't put in antennas, then yeah, use radiacs. But if you can, no, I mean, just as bad no matter what the frequency for the reasons I just mentioned. Yeah. So again, for UHF, 700, 800, VHF, whatever, if you have no choice, well, you have no choice. You have to run RADIACs. But if you do have a choice, no, it's just generally not real good.
Okay, so the next question, dealing with near-far effect, roughly how far apart should we be looking at for antennas in general? That's
well, Doug. Again, not only, yeah, it's a very good question, very, very good question. So again, not only from a near-far perspective, but also from a good design perspective, we recommend antennas should be located every 50 to 60, 50 to 60 feet apart. Because again, an antenna that's, that's covering 50 square feet, or has a 50-foot separation from the next antenna, which means about 100-foot radius, 100 to 120-foot radius. That means that antenna is going to cover, roughly 5,000 to 6,000 square feet. And you need enough antennas to deliver enough uplink gain signal to the BDA, because if you don't have sufficient uplink signal going to the BDA, the only way you're going to have strong enough signal to get out of the BDA to the tower is turn the gain way up on the BDA. And when you do that, you might get the signal to the tower, but you also run the risk of adding a lot of noise to the network, and network operators don't want noise. They want a good, strong signal with minimal noise. So the best way to do that is provide a stronger uplink signal to the BDA, and the way you do that is you put in enough antennas. And by doing that, you also then pretty much eliminate or greatly help with the near-far problem.
Okay, thanks. We have still a lot of questions. Any isolation documents? Oh, I've assigned this one to Jeff, so hopefully Jeff will see he has a question to answer. It's about design templates. Someone's asking, what is the best way to find out who the AHJ is?
Best way to find out who the AHJ is? Well, again, if there's an ordinance, generally the ordinance is labeled as coming from the agency. Now, again, that ordinance may not have very much technical information, and so you go, okay, well, here's an ordinance issued by the Blitzstark County Fire Department. And you call the fire department, and they go, we don't know. Well, then you have to say to them, okay, well, do you guys have your own radio shop? No. Well, who takes care of your radios for you? Oh, well, it's this group that works for the county. Ah, there's an indication. Probably the AHJ is not the network licensee. So then you have to make some calls to find out who is the network licensee, because that's probably where you're going to get the technical information. But generally, you're putting in an ERRCS system because there's an ordinance, and generally the ordinance document comes from and is labeled from whatever jurisdiction issued it. So that's how you'd find out.
Okay. I just want to point out to somebody on the call, I just responded to him, to Paul. I'm going to ask Matt to follow up with you after the call. There's a couple of more technical questions. Here's another question. How do you deal with multiple towers where each source has a tower?
With multiple towers where what? I didn't hear the rest.
I think it, how do you deal with multiple towers where each source has a tower? Not really sure about that one.
Yeah, well, I mean, yeah, there are many jurisdictions that have multiple towers, and depends on their network structure. Sometimes every one of those towers transmits the same channels. Other cases, each tower will transmit sometimes a subset of the the network-wide channels, but then some other channels of their own. For example, Orange County, California, who runs the network for all the HJs and jurisdictions are in Orange County. They have, I think, five or six towers, and some of them transmit different channels than other ones. Some of them transmit all the channels. It just depends on how they've got their network laid out. So again, that's maybe whoever asked that question maybe send an email either to Matt or myself. And if need be, maybe we have to get on a quick call. And again, happy to do that.
Yeah, you know what? We've gotten some great questions here, and I think it's probably time to say goodbye because we've held everybody a long time, and we do have a lot of the questions I'm seeing are a lot more technical. So to everybody who's waiting for your answer, Joe, Paul, Alden, Edward, we'll get back to you after. Oh, Amir, sorry, you asked one too. Thank you so much for asking all these great questions. It's really been awesome. And thank you, Dawn, for the fantastic presentation. As Dawn mentioned, we're going to send out a PDF to everybody. That'll make my life a lot easier, actually. I probably should have done that last time. Also, we have recorded this webinar, so I'll also send a link to the recording. And Dawn, do you want to say anything?
No, just thank you, Alliance, for selecting us to participate in this. I know you're going to enjoy next week's installment with Mr. Adams from PCTEL. As always, Charlie, thank you. And I guess the last thing, and Lisa, obviously, thank you for setting this all up. The last thing I want to say again, anyone who had questions that we ran out of time for, please, please, please don't hesitate to send email to Matt or myself. If you send one to me and I can't answer it, I'll demand, because one of the things we're very proud of here at Comba is we love customers and we love taking good care of them, and we promise we won't let you down.
Awesome. Thanks a lot, Don. And we all care about everybody having a good signal. My husband's a police officer too, so we all have a connection somehow to this. So we want to keep everyone safe. Thank you. Have a great day.
Right. Thanks, everyone, and
Thank you,
stay
everybody.
safe.
Bye.